Welcome back, and I do hope as ever you and your family are keeping well. So what we're going to look at today is we're going to look at the need for significant figures. We're going to look at decimal places and how you use these when you're writing numbers down scientifically. So to kick off with, I'm going to try and show you the importance of significant figures and why it's really important that you use them correctly. But as with a lot of things in physics, it really helps if you understand why significant figures are important. So you don't just learn rules, and I've looked at quite a few other people's YouTube videos, and they're all great, but quite often they just state rules. They don't really give a reason. So I'm going to try and show you a reason for using significant figures. So let's keep it very simple. Let's imagine we go for a walk, and we're going to measure how far we go. So we're going to start off here, and we're going to walk this way, okay, in this direction. So I suppose vector quantity, we're going in a straight line. Right, and what we'll do first is we'll walk 5 meters. Okay, so the first thing we're going to do is we're going to go 5 meters. But we're going to estimate how far we went or use a really poor measuring device. So we're not quite sure, and I'm making this ridiculously bad. We're going to go 5 meters plus or minus 2 meters. Okay, so that's our first little bit of walking. So maybe we might take a few steps and estimate to the nearest 2 meters. So there's our 0 point. 1, 2, 3, 4. I'll put 5 there. Okay. Now, where are we? Okay, well, we've measured our position to the nearest 2 meters, and we've done it to one significant figure. Okay, so I hope you're aware that that doesn't position us at 5 meters. What it does is it says, well, you could be at 5, but you could be 2 less. So I'm going to try and draw a sort of position so we put it about there, a 3 meter point. There's the 5 meter point. And we are definitely on or further than this ring that I've drawn. Okay, so that's the 3 meter point. But we could be at 5 meters plus or minus 2. So we could actually be here at the 7 meter point or anywhere in between. So I'll just draw a bit of a ring for that one to give you an idea of where we're positioned. So I hope you can see there that this number is to one significant figure, and because it's plus or minus 2 meters, there's some unknown about where we are. There's some uncertainty. Okay, that's all well and good, but now let's get ourselves a decent measuring tool and measure with a greater precision. So now, okay, let's walk a bit further and let's do it to 2 significant figures. Let's walk 1 meter plus or minus 0.1 of a meter. Okay, so we're going to do 1 meter further plus or minus 10 centimeters. So we're probably using a meter ruler here, or a meter rule, calibrated in 10 centimeter chunks. Okay, now I hope you can see what's happening. We're now going to be, well, 1 meter more, so that puts us here at 4 meters. Okay, or we could be here at 7, and we go 1 meter more, so that puts us at 8 meters. Okay, but the crucial thing is with this, that where are we? Okay, well, we could be at 8 meters plus or minus 10 centimeters. So I should really get a really thick pen here, but I'll draw the sort of ring that we're on. A bit tricky to draw this one. Try my best. Okay, now that should have a bit of thickness because we're 10 centimeters more or less around that point. But hang on, that's only if we were at 7 before. But what if we were at 3 meters before? Well, I think you get my point. We're now probably at 4 meters plus or minus our 10 centimetres, so I'll just fatten up the line like that. Okay, should really use a thick pen. So, I hope you can see what I've done here. Yep, this is to one significant figure and has a lot of uncertainty. This is to two significant figures, okay? So, which number messes up our results the most? Well, clearly, this one messes it up the most because we don't actually know where we are. We're somewhere in that sort of region. And can you see, by quoting your total distance, your total distance in two significant figures is totally meaningless, okay? Because the two significant figures gave us the little sort of margin of error here, okay? But it's the one significant figure one with the poor uncertainty that controls where we might be. It's the biggest error as well. So, if you were asked, what is your total distance here? Okay, you could say 6 meters. Yeah, you could say 6 meters. You'd have to quote your uncertainty, which is something for another video. Okay, but you certainly cannot give it to two significant figures, because when you deal with significant figures, when you get to the end of your calculation, it's the number you used with the worst number of significant figures that controls how many significant figures you're going to use in your answer. Okay, so now let's look at significant figures in use, and we'll do a little example of measuring something. So imagine I've got a ruler here, and I'm measuring the length of a pencil that I've put up against the ruler. Okay. Now, I hope you realise that because this one is calibrated in centimetres, we'll argue that we've lined it up correctly at this end, then we're probably plus or minus half a centimetre measurement. Okay, so we can see that the length of this one, so we'll put L, is equal to 6.5 centimetres. But we should do a better job there, really. We should say that it's about plus or minus half a division. So I'm going to put in brackets here, the length is equal to 6.5 plus or minus half a centimetre. Okay, now you could do it plus or minus 1 millimetre if you want, if the smallest scale on there is a millimetre. Not the point I'm making today. The point I'm making is that this number is to two significant figures. So we can sort of abbreviate that and say we've made the measurement to two sig figs. Okay, and if we just quote this number, okay, it's okay to say 6.5 centimetres to two significant figures, which lets us know that we're not in a position where we've measured the length like this, 6.5000 centimetres. Okay, now if we did that, we'd be measuring to a very high level of precision. It wouldn't be possible in this case, but there were students who might be happy to write that down. Okay, and if we look at this, we're measuring 6.5, and then we've got information here about even finer detail, about hundredths, and thousandths, etc. So if you look at this one, 1, 2, 3, 4, 5, this is to 5 significant figures. Okay, I don't think that's a good thing to do in this case, but I'm making it clear that these zeros here are significant. They give us some information about how finely we measured the length. Okay, we probably used some vernier calipers or something like that. If we did it like this, the length is 6.500 centimetres. Okay, you can see clearly now that that's 1, 2, 3, 4. That's measured to 4 significant figures. Okay, but I think the best thing to do is to say, look, with the ruler that we've got that is plus or minus half a centimetre, we can only really measure to 2 sig figs. So in this case, that lot, okay, isn't really correct, neither is that. Yes, you can quote your number to a higher number of significant figures, okay, but it's meaningless in this context because we're only using a ruler calibrated to the nearest centimetre, okay. It's interesting to note, by the way, I'm not quite sure why you would do this, but there are some ways of writing things down and some computers that might do this or screens that might do this. If we write the length as 6.5 centimetres, we could also write the length as this. The length is 6.5 centimetres. Okay, and other films that I've seen over the years make a big point about, are the zeros before the number or are they after the number? Okay, you'll notice the decimal is crucial here. Okay, so we've got a decimal and then we've got places after that decimal, and they are significant. Okay, you'll notice this one is here to 2 significant figures. And then we've got a 0 here, but that doesn't give us any information. Okay, this 6 is the number that begins to give us information about the measurement. So that 0 plays no part at all. This number here is to 2 significant figures. Now, there are shorter ways of teaching this. I do appreciate that. But what I'm trying to do is show you how it works. Some people just set rules and say, look, if you've got a decimal point and you've got zeros after the decimal point, they're finer measurements. They are each significant. If you've got zeros on this side of the decimal point, okay, leading zeros, shall we call them, they are not significant, if you're one of those people who actually wants a rule. Okay, but you could see we could add more and more zeros here. Old-fashioned calculator displays used to do that because they didn't just switch off. They were all set to 0, and then the numbers scrolled round, and these remained as zeros. I think when we used to get petrol from the petrol station as well, maybe it's still the case now, that you get zeros here. So it might be 006.5 litres, okay? And these zeros are not significant. So what I thought we'd do is we'd do an example to try and deal with this issue of zeros in a number and how that affects significant figures. And maybe you can try and work out how many significant figures are in these numbers as we go along. So here's my example. Let's take a measurement. I won't put any units on it. I'm just going to deal with the numbers now. And we get the number 200. Okay. Have a think about how many significant figures that is. But what if we got the number 201? How many significant figures is that? But then if we measure more precisely, so if we measure it as 200.0, okay, that might scare off a few students because they might go, well, why is that 0 there? Okay, really, I hope you're totally familiar with the fact that that 0 is really important. It tells us that we've not only measured to the nearest 1, but we've measured to the nearest tenth. It's a more precise measurement. Okay, and that leads to this. What about 200.01? How many significant figures is that? But here's the tricky one. What about if the number is this, 0.0020? Okay, so we've got some measurements here. I'm not saying that all measurements are the same thing, but this is a tricky one. Okay, how many significant figures are in each of those? So I hope you got the right answer. You might not have got the right answer here, in fact. Okay, now I'm I could go around in circles arguing about this one, and I'm not going to. I'm just going to tell you what the rule is. Okay, the convention is that if you've got zeros here, okay, not decimal places, then this is the number that we can see change in. It's not a 0, it's a 2. So this, rather oddly, is to one significant figure. One sig fig. Okay, if that's obvious to you, fine. But if it's not, just pause and think about it. Okay, these numbers haven't sort of scrolled yet, so we haven't really got any information here. Whereas this number, we can see it scrolled to 1, so we've got resolution down to the nearest 1. Okay, the more you think about this, the more of a tangle you can get in. So please just go with the convention. Okay, so here we go to the nearest 1. So we've got 1, 2, 3 significant figures. Now, what about this one? Well, we're measuring to the nearest tenth here, precision to the nearest tenth. So 1, 2, 3, 4 significant figures. And you can see where this is going to the nearest hundredth. 1, 2, 3, 4, 5 significant figures. Now, this final one. Okay, and I had to be very careful what I said in an earlier part of the video when we were dealing with decimal points. Okay, I've written up here precision versus magnitude. Okay, it's a bit difficult to explain what I mean by that, but these zeros here tell us that this is a very small order of magnitude, a very small number. These zeros here tell us that it's a much larger number. It gives us the order of magnitude, the sort of powers of 10. Okay, it doesn't give us information. It doesn't give us information. Okay, in terms of what those digits possibly could be. So they're not significant. Okay, so it's interesting that that doesn't tell us anything, that doesn't tell us anything, that doesn't tell us anything, other than how big the number is. It's here the numbers start to change. And we've got a 0 after it, so we know we're measuring even more precisely. So, 1, 2 significant figures. Now, I've got to be careful not to get myself in a bit of a trap here, but if you're someone who likes rules, as it were, it's quite complicated, okay? These zeros in front of a number, and we dealt with that earlier on with my sort of petrol station example, are not significant. The decimal place is not relevant to that, okay? However, if we have a number in front of the decimal, like this, and then we have decimal places, all of those become significant, as it were. Okay. However, here we haven't got a decimal place marked. Okay. It doesn't say point and then something. Okay. So the convention here is to say that that's the number that carries some information. We don't know about those. Okay, so that is only to one significant figure. Now, that's not a brilliant way of explaining a rule, but I think the best way to look at this, okay, is to look at this example, okay, and compare it to this example and spot the difference there in terms of how we quote significant figures. But just before I finish on this one, there's one other little bit I'd like to do. Okay, students of mine who are highly mathematical are very happy to write answers down like this. So they might write down, I'll just put e.g. here to separate it. Okay, so there's our example. They might write down an answer like 2/6 meters, or okay, they might go to 1/3 of a meter. Now, I've got to be really careful what I say here, okay? I'm going to say it. Don't use fractions as an answer in A-level physics, okay? Don't use fractions. There are times when we use ratios, okay? But a mathsy person or mathsy student, with respect, would be quite happy with 1/3 of a metre. But think about what that means. Okay, what they've done, and we have arguments about this in class, what they've done is they have said it's 1/3 of a metre. What they mean is it is 0.333333 recurring metres. Okay, and if they're saying that, they're actually quoting that number to an infinite number of significant figures. So my message to you is understand significant figures, okay? Understand precision, and when you quote a number, it's best to write it down as a decimal, so you are stating to how many significant figures and to what precision you're measuring that number. Oh, just before we finish on this, I forgot to mention something. It's this one, okay? We were talking about magnitude of this one, so it's a small number, sort of low powers of 10 is kind of a way of thinking about it. And you may be concerned that that and that are not significant. But of course, what we're going to do is we're going to put this into standard form. And when we put it into standard form, you'll see very clearly that we will have 2.0 times 10 to the whatever it is, 1, 2, minus 3 here. Okay, and that 2.0 will give us the precision of the number, okay, with the times 10 to the minus 3 on it. But it's 2.0, it's two significant figures, and the 10 to the minus 3 is just the magnitude of that number. And I'm going to do an example of that in a minute, but this shows it quite nicely. So now let's look at standard form and significant figures, and it's not as bad as you think. So imagine we measure a number and we get this 3.6 times 10 to the minus 3. Okay, won't bother about units, that's not the important bit today. So how many significant figures have we got there? Okay, well, some of you will know, if you know me well, I'm an absolute fan of engineering notation, and this is engineering notation, so I can immediately say milli. The disadvantage of using engineering notation, where you could have more numbers here and powers of 3, 6, 9, etc., is that it's a bit tricky to look at how many significant figures there are. So have a think about how many significant figures in that number. And it's 3.6. That's the magnitude. Yeah, 3.6. So this one is to two significant figures. Now, I'll just show you why that is, if you're not perfectly clear. 0.0036. Okay, so these just tell us that the number's very small, that kind of magnitude. That tells us the precision we've measured to. So there's 1 there, there's 2 there. There we go. It has to be to two significant figures. Now, let's have a look at some other examples just to make this really clear. Okay, so what happens if we measure a resistance and the resistance is this large? So I'll put the units on there. I'll put a comma in there just to make it clear from my teaching, though you shouldn't really put commas in. And of course, if you're from overseas and you study in the UK particularly, for heaven's sake, please don't put commas in, because for you guys, a comma means a decimal point. I argue this with my students in the UK. Look at the pocket calculator, okay. If it's a decimal, please use a point. Okay, but I'm doing that just to show you the separator there. Okay, so how many significant figures have we got here? Is it 1? Is it 2? Is it 3? Is it 4? Is it 5? 1, 2, 3, 4, 5. Sig figs. Okay, well, I think you know this well enough now. Okay, It's very tricky actually to know. It's tempting to say 1, 2, 3, 4, 5 sig figs, but do you remember sometimes you need a convention, and the convention is that if we don't have a decimal place, okay, we don't know whether these were measured, okay, whether there was any precision here. So I'm afraid it's just the 2 that counts here, okay. This one is to 1 significant figure. And I've got in my notes to myself, this is poor. What I mean by that is it's not a brilliant way to write a number down. It makes it a bit unclear of how many sig figs there are. So we have to sort of use convention, as it were. But what if we write it down like this? So the resistance is equal to 2 times 10 to the 4 ohms. Okay. Now, that's standard form. Okay. I, as you know, like engineering notation, so I like 20 times 10 to the 3, so I can immediately go 20 kilo ohms. But that does have a problem dealing with significant figures if you're not very confident. So it's a good idea always to quote numbers in standard form if you're finding significant figures, something important to you in a calculation. Okay, and I think it's pretty clear there. There it is. Okay, this is to 1 significant figure. Yep, because that is just a multiplier. That's just an order of magnitude, as it were. Okay, but tell me what you think of this. Okay, a different measurement. We measure the resistance and we get 200.0 times 10 to the 2 ohms. Okay, so you can see there, times 10 to the 2, so there's another 2 noughts there. It's looking similar. How many significant figures is that one to? Well, we've got some information now about the precision here. Yeah, so 1, 2, 3, 4. That's just the multiplier. Yeah, so this one is to 4 significant figures. Yep, because we've got information here in the tenths times 10 to the 2. Okay, so that leaves us with just saying, well, let's make it easy. Let's just say that the resistance is 20 kilo ohms. Okay, and this is a tricky little fella. Okay, because you might think, and we're probably going to have arguments about this one, okay, but I'm pretty certain I'm right here. Kilo is saying, it's a lazy way? No, it's a brilliant way of saying times 10 to the 3. Well, if that's the case, okay, then we can say that this is to 2 significant figures. I'll get a better pen. There we go, 2 sig figs. And finally, what would happen if we did this? The resistance is 20.0 kilo ohms. Okay. Well, if this is getting a bit dull and a bit repetitive, great, because it means you understand it. There we go. There's our multiplier, the kilo times 10 to the 3. Yes, we're in engineering notation. I do like that. Okay. 1, 2, 3 sig figs here. So I hope that helps you understand a little bit better how we deal with numbers like this and how we can say to how many significant figures is the number quoted. So now let's do a quick example. And what we'll do is we'll add some numbers and look at how we should quote the number of significant figures at the end of our addition. So, a quick example. What we'll do is we'll take, you could imagine their lengths if you want, but it doesn't really matter. Let's add 13.4. You can imagine it's meters if you so wish. And let's add that to 2.2 5. Okay, so you'll note straight away I've got two numbers here quoted to different numbers of significant figures. I've got 3 of them there, and I've got 4 of them there. Okay, so let's do it in the old-fashioned way. So 13.4 added to 2.255. Now you'll notice we haven't got the noughts there. We didn't put those in, so we haven't got information about 4 or 5 or whatever significant figures. Yep. Gosh, this takes me back to my days in primary school. So we had to do that, and we had to do that, and we weren't allowed a pocket calculator. Okay, and then we had to do the 5, and we had to do the 5 anyway. 5, 5, 6, 5, 1, and check the decimal. Okay, I tend to put the decimal place in sort of in up in the air. I know that's not necessarily conventional, but it's clearly seen by an examiner. Okay, so am I going to write the answer down as 15.655? Okay, and no, I'm not, because you must remember, of course, that we always quote significant figures of our answer, okay, governed by the worst number we had. That's the worst one, the 13.4. Okay, so these guys aren't any help to us. I hope I sort of explained that at the beginning of the video. If it isn't perfectly clear, perhaps have another look at that, or just terrible teaching this. Just go with it. Okay, the convention is, because it does make perfect mathematical sense, to limit how well you describe the answer in terms of the worst number of significant figures you have, or the precision in this case. Okay, now, so what do? We do all of our maths, and we get this answer, 15.655. That's important. Don't round. Okay, but when you've done all your maths and squaring and multiplying, etc., round right at the end only. Okay. Otherwise, you get a problem called a rounding error that I won't go into in detail. But if you're rounding one number, then another, then another, then another, okay, you can bring errors into your final answer. So it's a bit of a weird one. Work with what you've got, okay, and then write down the answer. Now, this is important, yeah, that you look at these numbers and you say, I've done it purposefully, so there's a 5 there. Okay, quite a nice way to do it is put a 9 there as well. Okay, so your answer, the answer here, yeah, will be 15 point, and because of those 5 5s, 7. Okay, so we've rounded right at the end. We've looked at the worst number of significant figures we've got, and of course there's a precision there of tenths, and then it's a good thing at the end to say 2, 3 sig figs. So don't be tempted to make your final answer 15.655. So I'm sure you got that absolutely fine, but I want to do one more example just to make the point. Okay, so let's calculate a velocity. And we're going to do this properly, of course. So our formula, velocity, is displacement divided by time. Okay, it's not the time for this, but I didn't want to say distance because it's a velocity, so it's a displacement, and we use that letter S for displacement. I always think about it as separation. Okay, and we need some numbers to work with. So let's say that our displacement was equal to 103 meters. Okay. I won't put plus or minus on there. I'll just say 103 meters, because by convention, it's plus or minus 1, I guess, with this last digit. So you should just be going, yeah, 3 sig figs, no trouble at all. And we measured the time, and we got the time as 12.15 seconds. Okay, So you'll notice they're down to hundredths of a second in terms of the precision, and 4 significant figures. Okay, so remember, don't do any rounding now, just crack on and do the maths. So the velocity is equal to displacement 103 divided by 12.15. Again, trying to make my decimal very clear there. Okay, you divide that out, and your calculator, I think, gives this sort of nightmare. 8.47736662. Okay. Now, again, with respect to GCSE students, it's difficult to explain to them. They're quite happy to write that down. I hope you feel incredibly uncomfortable about writing down that number for a number of reasons. It's got no units for a start, but also we've gained lots and lots of precision from somewhere magical. Okay, and also we've gained, therefore, significant figures. Okay, so if you remember the kind of way of doing this, the sort of rule of the game, yeah, is you quote your answer to the worst number of significant figures in the measurements that you used. Yeah, so quote your answer to the worst number of significant figures in your measurements. So we look at our measurements and we go, okay, got this one here, 3 sig figs, got this one here, 4 sig figs. That's the one that kind of messes it up, technical term, clearly. Okay, so in this case, we've got 3 sig figs here, which is our worst. Okay, so we can only quote our answer to 3 significant figures. So we can say that the velocity is equal to, and I did this one purposefully, round right at the end only. Okay, so you can see that we can get rid of all of those. 1, 2, 3 significant figures. So have a look at that lot. Okay, and then you've got this 7 here, so that's where you do the rounding. So the velocity is 8.48 meters. Oh, perhaps I should do it properly like that, meters per second. Okay, and you can say after that to 3 sig figs. Obviously, in this case, it has to be. Okay. If you had more significant figures here, like 10 and 10, you could still quote to 3 significant figures. The choice is yours, but you can't quote more significant figures than the worst measurement that you've got. So I mentioned a minute ago about rounding errors, and that you round right at the end of your calculation. And it can be a little bit tricky to round, and I'll show you why. So we're just going to quickly look at rounding plus rounding errors. Okay, so I said when you get a calculation, use the numbers you're given. Okay, and if you get part way through a calculation and you get a whole string of numbers on your calculator, don't switch into significant figures or rounding at that stage. Keep going and keep going and keep going until the end. Then look at the horrendous string of numbers you've got and then quote it to the correct number of significant figures. Now, that can be a bit tricky, and I'm just going to quickly give you some examples here. So here's a number, 6.6289. Okay, and if you quote that number, 1, 2, 3, 4, 5 significant figures. Okay, so this has got 5 sig figs. Yep. But what would you do if the number that you worked with, the numbers you worked with, the worst one was only to 4 significant figures. Okay, so this is where you do your rounding, and I think this is going to become obvious. 6.629 is to 4 significant figures. But hang on, what would happen if the worst number that you worked with at the beginning was only to 3 significant figures? Well, again, right at the end you do your rounding, 6.63, and that's to 3 significant figures. And let's keep going, though you can probably see where I'm going here with this. Okay, to 2 sig figs, well, that's easy enough. 6.6 to 2 sig figs. And I think if you had to do that straight away, you got the number at the top and had to do 2 sig figs, I think it's pretty obvious, 6.6. You might have to think a little bit if they said, quote that number to 3 sig figs, but then you'd see that the effect of the 9 on the 8, it doesn't have an effect on the 8, so it's the 2 that scrolls up to a 3. And finally, what if you have to quote this to 1 sig fig? So an early measurement you worked with only kind of had the single digit in it, or the single significant figure. Okay, and remember that it doesn't have to, you look at where the decimal point is as well, because it could have been 0.01 or something you were working with. Still a number to 1 significant figure. Okay, so this to 1 significant figure is 7. Okay, please don't write 7.0 there, okay, because then that would be to 2 significant figures. So that really comes into play when you finally got your answer on the calculator screen and you have to compare it to the worst number you started with in terms of significant figures. And if it was 1 significant figure, that is your answer. But it's good to say that after it, to say where you got that number from. So if there's anything that makes the importance of significant figures clear, this example is it. So what I've said is you must not confuse decimal places with significant figures. The hint's in the name, they're significant. They're important in our measurement. So what I've done is I've taken a measurement here where x is 12.34. Okay, I'm sort of kicking myself really. I wish I'd made that v for a velocity, because I'm now going to square it. Okay, so x squared is 152.28. Why I'd like v, of course, is we do this with kinetic energy, don't we? We have half mv squared. So this is an important lesson for working out kinetic energies, if nothing else. Okay, so I then measure again, and I get 12.35. And look, that 4th significant figure is the one that has changed. Okay, but if I square this number by changing the 4th significant figure, if you look carefully, the 1's the same, the 5's the same, the 2's the same, but this 2 goes to a 5. It's at the 4th significant figure that we see the change. Okay, so I've quoted all of these to 2 decimal places, but that's not helpful. Okay, a change in the 4th significant figure is where we see a change in the squared. Okay, so we must quote to 4 sig figs. So quote your answer to 4 sig figs. Don't, whatever you do, be tempted to quote to 2 decimal places. So not to 2 dp's. Okay, and I hope I've made it clear there that the reason for that is that the numbers are to 4 significant figures, and if you look at it carefully, a change in the 4th significant figure has an effect here at the 4th significant figure. So there we go. You should quote your answer to, perhaps I should have done that in blue really to stick with my colour scheme, you should quote your answer to 4 significant figures. Don't do it in terms of decimal places. Okay, so now for a tricky bit, and I've left it right at the end to deal with. Logarithms are something you need to get your head around at A level, and we use them quite a bit. And you might remember we have log to the base 10 and log to the base e. Okay, it's not a particularly easy concept, but spend some time trying to get your head around, okay, that the logarithm of a number is what you'd have to raise 10 to get that number, okay, or what you'd have to raise e to get that number. But anyway, I'm not a maths teacher, so I'm not very good at that sort of thing. But what I want to show you is it tells you something about the power that you're raising a number to, 10 or e, for example. Okay, so you'll be pleased to hear that it doesn't give you information about the precision of the data. So we're not going to use significant figures at all when we quote the logarithm of a number. Yeah, that power that we're raising 10 or e to. And there you go, there's your rule. Okay, but I need to explain this to you. So let's have a look at some data. So x, okay, and then we'll take the log of x. So I'll draw a little table here. Pen's not brilliant. It's an end of term pen running out. Okay, and here's the log. I'll write it like that of x. So I'm doing the logs to the base 10. Okay, so let's imagine x is 14.2, and then it goes up a little bit to 14.3, and then you can see what I've done here: 14.3 times 10 to the 3. Okay, so if you take the logs of those, just look carefully. This is a bit more than 10. Okay, a bit more than 10. Okay, and then here you've got the 10 and the 1,000. Okay, so kind of a bit more than the 10,000, as it were. So a bit more than 10. So this one is going to be 1 and a bit, 1.152. Bit more than 10, 1.155. And then here's the interesting bit. Okay, there's the 10, and there's another 3 orders of magnitude, so that's sort of 10,000, so 4, yeah, that's the 4.155, okay, and what you'll notice is that when we do this, okay, if we change this number here, okay, so the first decimal place, we've gone from 2 to 5. Okay, these 5s have stayed the same. Okay, so I'm just pointing out that by changing this one here, yeah, I've kept the 3 the same there. So by changing that first decimal place, so if we change this, yep, you'll notice that results in a change, not in this column or that one, but you get a change here. Okay, so what you'll notice is that it's this third decimal place that's changing when we take the log of x. So, quote, using decimal places, okay, and quote log x here to 3 decimal places. So I hope in that example I've explained to you the sort of mathematical reason for not using significant figures but using decimal places. And secondly, I've shown that scrolling this number here, maybe I should have made that one a 4 to really make the point. It has an effect not here, not here, not here, but there. It has an effect at the third decimal place. So I do hope you found that lesson on significant figures and finally decimal places and logarithms useful. I know it was quite a long one, but what I wanted you to do was to see lots of examples and also to understand why we work in the way we do in physics with numbers. Anyway, I'm sure I'll be making another video lesson before long. Enjoy your physics, and I look forward to seeing you then.